This is a workshop choosing a statistical test, and we cover the example data we use, what you need to choose a statistical test. We use examples to demonstrate how you go about choosing a statistical test. And then we finish by talking about assumptions, because that'll affect what test you end up using in some cases. So if you've contributed to our questionnaire that goes along with this workshop, it makes it easier to understand the examples we've got. So this is the questionnaire. We've got a Likert scale questions at the start. We've got a nominal type question here, a yes/no question. You can put in a number in here and in here. We've got gender, age, the same question at the start repeated. Another yes/no question, another categorical nominal question, another sort of categorical question, and then we've got a sliding scale here. And finally, these three questions repeated again. The results are in a spreadsheet that you might be able to view. And this is useful to view them so that you get an idea of what types of questions produce what type of data. So for instance, Likert scale data will produce numbers in 1 to 5. This yes/no question here is produced a 1 and a 2 type of data. The steps question and how long it takes you to sing happy birthday give numbers, but they can be quite high numbers, and so on and so forth. I've picked out 5 hypotheses from this questionnaire, and that's the data that we're going to use today. So what do you need to choose a statistical test? You need 5 things. The first thing we're going to talk about is a hypothesis. So I'll give you some examples of those. Then you've got to identify types of variables. So it's helpful to identify dependent and independent variables, or if your hypothesis isn't testing dependent and independent variables. Again, I'm going to give you examples. I'll talk about the type of data. That's really important. Sometimes we need to consider if there are paired or repeated measures in the data. And we also need to consider, in some cases, the number of groups. So we're going to become familiar with all these terminologies, so don't worry if you don't understand them just now, over the next few slides. And then once we've done that, we're going to use a statistical test web page to choose a test for each hypothesis. This is R1 here. There's lots of versions of these stats choosers websites and flow diagrams and trees, etc. This is the one that I'm going to use today and teach you to use in the workshop. So let's start with hypotheses. It's a really good idea for you to write a hypothesis, even if you don't write it in the final report that you're producing. It's a good idea to write it because it forces you to identify what are the variables that you want to put into a stats test. So the first hypothesis I've pulled out as the questionnaire is here. There will be a difference in time spent singing happy birthday. We ask people to time themselves singing happy birthday. That's a measure, that's a variable. That's one variable that we're interested in. And then the other variable that I'm interested in is whether or not people enjoy singing or they don't enjoy singing. So that's my 2 variables there. The other thing that writing a hypothesis can force you to do is clarify what you're looking for. Are you looking for a difference, an effect, a correlation? And sometimes that will help you decide the stats test. So here's 2 more hypotheses I've pulled out of the questionnaire. So B is that enjoyment of filling in questionnaires is different at the start, middle, and end of a questionnaire. So I know that I'm looking for a difference between these 3 time points. And then C is that daily step count is affected by gender, age, and dog ownership. So I know that there's 3 variables there that I'm hypothesizing might affect someone's daily step count. You get different types of hypotheses. So some people might choose to write just a null hypothesis, and that's denoted by a capital H and a subscript 0. And that might be something like gender does not affect pet preference. So it's phrased in a sort of not negative way, but like there's nothing going on, there's no effect, there's no correlation. That's the way a null hypothesis is written. Alternatively, you might write an experimental hypothesis, also called an alternative hypothesis, denoted by a capital H and a subscript 1. And that's really, really similar to a null hypothesis, except it's stating that there is an effect, or there is a difference, or there is a correlation or association. And sometimes you can write both, and it's quite common practice to put the null hypothesis first and then the alternative hypothesis. The reason you might want to write a null hypothesis is that it then makes sense when you run a statistical test. Because that null hypothesis at the end of a statistical test is either rejected or accepted, depending on what the p-value you get from a stats test. So to give you an example, here we've got a null hypothesis, which is name length. So we asked people how long their name was in the questionnaire. The name length is not correlated with how someone feels about a stats workshop. So remember, we had that smiley face in our questionnaire. And we're saying that these 2 things aren't correlated with each other in our null hypothesis. So what we would do, we would run a stats test. And if the p-value is less than 0.05, then we reject that null hypothesis. We say, okay, this isn't true. It's not true that they're not correlated. If we get a p-value which is more than 0.05, then we have to accept this null hypothesis, and we have to accept that there's no correlation between our 2 variables. That's how null hypothesis statistical testing works. During this workshop, it is quite interactive. I advise that you take some notes. So for each of these 5 hypotheses, you might want to write down what the dependent and independent variable is, the type of data, if there's repeated measures, and number of groups. Because this is then going to help you understand how we choose a stats test at the end of the process. So we've talked about hypotheses. Let's talk about identifying variables. So we want to identify if there's any dependent or independent variables in these hypotheses. We've got these scenarios we've got. Now, stats is a little bit annoying because we use different terminology in different disciplines. So I'm going to give you alternative terminology just in case you've been studying stats before, and you can hopefully relate to it. So I'm going to use the term dependent variable, but you might have heard it called a response variable or an outcome variable or just an outcome before. It's the same thing. It's a dependent variable. Also, I'm going to talk about an independent variable. But again, you might have came across an independent variable being called a predictor or factor. So how do we go about identifying what variables are dependent variables and what variables are independent variables? Well, we have to think about the relationship between the variables. The dependent variable is changed or affected by the independent variable. So put another way, the independent variable is causing the dependent variable to change. Of course, there's another possibility. In some situations, there is no dependent or independent variable. So in other words, there is no cause and effect. Now, if you have no idea what I'm talking about, don't worry, because we're going to do we're going to look at some examples, and hopefully that will clarify this phenomenon. So here's an example. Our first hypothesis here, where we've got this effective singing attitude. So our singing attitude is whether you enjoy singing or not, on how long it takes you to sing happy birthday. The dependent here is singing time, and our independent is singing attitude. And that's because we're hypothesizing that the independent singing attitude affects how long someone takes singing. It has an effect on this dependent variable, which is singing time. So now what I want you to do is identify the dependent and independent variables in each of these other scenarios. Before you do that, just remember that in this first example, time singing happy birthday is measured in seconds. It's just the name of the variable. We've got the variable time in the second example, but it's a very different variable. In the second example, it's when you answer the question, how much you enjoy filling in the questionnaire, and it's time as in start, middle, and end of the questionnaire. So what I want you to do is stop the video and tell me what the dependent variable is, what the independent variable or variables are in each of these questions, or is there no dependent or independent variable? Okay, so we've done the first one. Here are the answers for the rest of them. So the first one, what we're saying is that the time affects how much you're enjoying filling in a questionnaire. So maybe we might be imagining that, say, at the start of the questionnaire, you're quite enjoying filling it in. By the end of the questionnaire, you're not really enjoying it as much. So that means that the dependent is how the measure of enjoyment of filling in the questionnaire. So those 3 questions that we kept asking them. Whereas the independent is the time. So the time is affecting the dependent. C, we've got the dependent is how many steps someone takes each day. And we're hypothesizing that that's affected by 3 variables. So this is where we've got multiple variables. That's quite a common situation. So our independents are age, dog ownership, and daily steps. So there's 3 independents there. This one, we're hypothesizing that depending on your gender, you will have different pet preferences. So therefore, the independent is gender, and it's affecting your pet preference. So the pet preference is the dependent. So there's a cause and effect in all of these ones. Now, when it comes to the last one, if you think about what one affects the other one, it's quite hard to answer that question. So if you thought, okay, does the length of someone's name affect how someone is feeling about a stats workshop? That doesn't really make a lot of sense. And similarly, does the way that someone's feeling about a stats workshop affect the length of their name? Again, it doesn't really make sense to say either of those. Although you could argue against it. So what we're saying here is that there's no dependent or independent variables. And that's going to really help us choose our stats test at the end. The third thing you need, and I would say that this is probably one of the most important thing to consider when you're choosing the stats test, is the types of data. If you're an SPSS user, you'll you might be aware of these types of data which come under measure in SPSS. I'm going to stick to those types of data, although there are other names for these terminologies. I'm going to talk about nominal, ordinal, and scale data. Nominal is sometimes called categorical data, and scale is sometimes called continuous scale data. So we need to identify what type of data our measurements are. So let's take some examples. Nominal data is it's basically categorical data, and a really common example of that is gender. Another example would be if you have treatments in, say, an experiment, or if you're working with people and you're giving them different treatments, you're categorizing those treatments. In our questionnaire, we had a question which was, do you enjoy singing? Yes or no. A yes or no question is a nominal type of data. Another type of data is ordinal. So anything which is a category, but it has a really obvious order, is ordinal data. So we've got Likert style answers in our questionnaire. These questions where we ask people how much they were enjoying filling in this questionnaire. These were done on a Likert scale, which I'm sure you've came across before, strongly disagree to strongly agree. And then what happens is we assign these to numbers, and it's the numbers that we use to analyze. That's a really typical example of ordinal data. Other examples would be degree classifications, so first, 2, 1, 2, 2, third, or places in a race. Did you come first, second, third, fourth, etc. The third type of data is scale or continuous scale. And you recognize scale data because you've got many possible values. So unlike Likert data, where you've just got, say, 1, 2, 3, 4, 5, and it can only be those 5. With scale data, it's almost like any value is possible. So think about if you were taking temperatures of days, you can, it could be 10, 10.5, 15, 23.6. Lots of different values are possible. And the same with weight. Weight would be another example of continuous scale. In our questionnaire, we asked people to time themselves singing happy birthday. And then we've ended up with data like this. So you can see there's quite a variety there, 10, 12, 18, 35. We've got a 10.5 there, 11.6. So lots of possibilities of data. What we're going to do now is identify the type of data in each of these scenarios. Before I do that, though, I'm just going to explain something about Likert scale data. So I said that Likert scale data is it's got a possibility of 1, 2, 3, 4, or 5, and we can see that in these 3 columns here. So I would always treat this data as ordinal data. Sometimes some people are a little bit stats cheeky, and they treat it as scale data. It's dependent on your discipline whether that's acceptable for you to do or not. What's more acceptable is if you take the mean of these 3 questions. Then you end up with data which behaves more like scale, and it's more acceptable to treat it as scale data. So what I mean by it taking the mean, let me see if I can just insert a column here. We'll call this the mean. So mean's just another word for average. And then if we type in equals average, we're going to take these 3 numbers. We get an average of 2. So 4 plus 2 plus 1 is 6. Divided by 3, we get 2. And we do that all the way down our column. And it would be this column that we use in our analysis. So let's identify the type of data in each of these examples. We've got the time singing. So that's this time singing happy birthday. Now, we've measured it in seconds, and people could enter like 10.5 or just 11 or 26. That's scale data. Any value is possible. And in theory, you could have a really high value. Whereas the group, so whether people enjoy singing or don't enjoy singing, that's nominal. So we've got two different types of data there. What I want you to do now is identify the type of data for each of the variables that we've got here. So these two variables here, these four variables in this one, the two variables here, and the two variables here. And then we'll give you some answers. So you can stop the video here while you think about that. Okay, so here's some answers. We've already done the first one. The second one, we asked people to fill in these questions at the start, middle, and end of the questionnaire. So start, middle, end, that's a categorical type of data. Now, I'm going to say that that's nominal. You might have said that it's ordinal because start, middle, end has a logical order. And that would make sense, right? However, we've only got 3 time points. So some of the stats tests where we use ordinal data, they need more than just 3 time points. So that's why I'm saying that time is nominal. And I hope that that's helpful for you because you might come across that in your own data. The enjoyment of filling in questionnaires, that's ordinal as well because it's on a Likert scale. But we had multiple Likert questions. We had 3. So what we would do is take the mean, the average of those 3 questions, and then we would use that column of data and we would treat that as scale. Since it's a mean, it behaves a bit more like scale. That's acceptable to do. If you find that hard, don't worry. Hopefully the other 3 were a little bit more straightforward. Gender, male, female, prefer not to say, non-binary, that's categorical and it's nominal. Age, we've asked for age in categories. So as in 18 to 20, 20 to 25, 26 to 30, 31 to 35, etc. So age is an ordinal type of data. If we'd asked what a person's age was, and they had to write 31, 22, 66, then our data would be scale data. Dog ownership is nominal. It's a yes-no question, which are always nominal. And then daily steps, we treat that as scale. I say that we treat it as scale rather than it is scale, because some people would say, well, it's not really scale, it's actually count data. And that's because you can't get decimal points in it. So you're unlikely to get 10,100.6 or 132.7 of a step, right? So they're always going to be whole numbers. So it's actually count data. But they're such big numbers that they behave like scale. Pet preference and gender are both nominal. Right? They're categorical. Cat, dog are both male, female, prefer not to say and other. They're nominal. Oh, sorry. And then the length of name, we didn't ask someone how many letters are in their name. We asked them to count the number of letters and then put it into a category that we had. So that's actually ordinal in that case. And then how someone's feeling about a stats workshop, We ask them to use the slider to make a sad or happy face, and then we translated those faces into 1, 2, 3, 4, 5. So those numbers 1 to 5, they're ordinal, very similar to a Likert style question. Right, the next thing we need to think about is whether we have data which is paired in any way or whether it's repeated measures. You get paired or repeated data if people or samples or the data, it can be paired or grouped in some way, or you have something where it's been measured more than once for the same thing. Right, so maybe that's a little bit theoretical, so I'll use some examples to illustrate that. Let's say you had a weight loss study and you had recruited twins to this study so that you can control for genetic differences. So you put one twin on one diet and then measured their weight loss, and you put their sibling, their twin, on another different diet and measured their weight loss. So those two pieces of data, the two weight loss, those would be paired, they'd be matched data. And that's because you want to compare one twin with another twin. So twin studies are a really typical example of paired data. Another example would be if you've got people doing a pre and a post test. You might even have people doing a pre, post, and maybe a delayed test. So there you've got paired data if it's just pre or post, or repeated measures if you've got pre, post, and delayed test. We're measuring people for the same thing. It would have to be the exact same test that you're giving those people, or the same questionnaire. Another example would be if we have rivers, just to have something that's not a people example. And let's say that we're sampling each of these rivers once a week for 4 weeks. So say you've got 100 rivers and you're visiting them, all of them every week, and we're doing that for 4 weeks. We then want to compare each of those 4 samples with each other. So we're controlling for river, let's say, the difference in rivers. So that would be repeated measures because you've repeatedly measured each river. You've repeatedly measured it 4 times. And repeat measures and paired data is the same as our independent and dependent variables in that we have alternative terminology in statistics depending on what discipline we're in. So just in case you've came across this, repeated measures are sometimes described as a within subjects design because you're comparing within the subject. So you're comparing the same person's pre and post test, let's say. Paired data is sometimes called matched data. So with that in mind, we've got 5 studies here, but only one of them is a repeated measures design. I want you to think about which one of these have we taken the same measure multiple times from a person. So you can stop the video and have a think about that. Okay, here's the answer. It's study B, the effective time on enjoyment of filling in questionnaires. And that's because what we've done is, if we just go back to our survey, at the start of the questionnaire, we measured everyone for how much they're enjoying filling in this questionnaire. Then halfway through the questionnaire, we asked the exact same thing. So we're measuring them again for how much they're enjoying filling in the questionnaire. And again, we measure them for the same thing at the end of the questionnaire. So that's repeated measures. The rest of these scenarios, they don't have paired data or repeated measures. And that's because, so on the first one, in case you were thinking that we were comparing times of people who enjoy singing and don't enjoy singing, we can't have the same people that enjoy singing and don't enjoy singing. It's different people. So that's not paired data. This one might have tripped you up, and you might have thought that, okay, so we've got two measurements here, but they're measurements of different things. We're measuring the name of length, and then we're measuring how someone feels about a stats workshop. So although those pieces of data might be connected because they're from the same person, they're different measurements. So they're not paired or repeated measures. Last thing we're going to consider is the number of groups we've got. If there's a nominal variable, so we went through and we looked at what variables were nominal before, then we need to consider sometimes how many groups it has. And this can be, this will be more obvious when I show you. It's actually quite simple when I show you, just on theory. So for instance, this first example, we've got a nominal variable, which is our singing attitude. We grouped people according to whether they enjoyed singing or they didn't enjoy singing. So that singing attitude variable, that's got two groups, right? Those who enjoy singing and those who don't enjoy singing. Again, just a little word on terminology. Sometimes people call groups levels. So they talk about, oh, singing attitude has two levels to it. What I want you to do now, for any nominal variable, so that's gender, time in this one, gender in this one, dog ownership, and pet preference, I want you to think about how many groups are in each of those variables, and then we'll go over the answer. So you can stop the video now. Okay, so this first nominal variable we had, which was time, i.e. the start, middle, or end of a questionnaire, has three, right? Start, middle, and end of a questionnaire. That's the three groups. Gender, we've actually got four groups here because we're going for female, male, prefer not to say, and non-binary. And that's quite common in questionnaires now. So that's got four groups or levels to it. Dog ownership has two, so yes or no. And then, in case you were wondering about age isn't actually nominal. We said that that was ordinal. Let's just say, though, that you don't manage to get your questionnaire out to a wide variety of people, and everyone you question, that fills in your questionnaire is either between 18 and 29 and 30 and 39. In that case, you'd have to start thinking about how many groups age has in your data. So even though we can say age has 7 here, we intended it to have 7, it might be that when it comes to your data, you only have 2 groups. And then your data is going to behave a bit more like nominal data rather than ordinal. So watch out for that one. Our pet preference has 3, cat, dog, both, and gender we've already seen has 4. Just another last word on name length and feelings about the workshop. So these aren't nominal variables. We intended them to be ordinal variables. So we would say that name length currently, the way we've intended it to be collected, it's got 9 categories. So this 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's got 9 categories. And the feelings about the workshop has 5 categories. It's got 5 groups, 5 levels. So if we got people filling in enough of these, so we've got enough spread of long and short names, and we've got enough happy and sad faces for our feelings about the workshop, we can continue to treat the data like ordinal. However, just like age, if there's fewer groups, we might have to change our plan on what stats test we use and treat the data as nominal data. Right, we're ready to actually choose a statistical test now. We're going to use this which statistical test, but you can use other ones that you've maybe used in the past and are a bit more familiar with if you want. What we need to consider when we're using this then is the things we've just talked about. Are there dependent and independent variables? We might have to consider how many independent variables there are. Is there just one or is there more than one? The types of data, nominal, ordinal, scale. The number of groups in the nominal variables. And whether we've got a design where we've got paired or repeated measures. So what I'm going to do is an example using the first hypothesis. Then I'll give you some hints on how to choose the test for the second one, and then you can have a go at the last three, but I'll give you the answers after each one. So this is our first example, the difference between groups, those who enjoy singing and don't enjoy singing, on time singing happy birthday in seconds. To do this, what I'm going to do is it'd be nice if you could see the slides at the same time as the stats chooser. Let me try and get my computer to work for me. Just going to make that a little bit bigger. There we go, we can see it a bit better. So the first thing that I'm going to consider is the dependent variable, my time singing. So I've identified that that's my dependent. I do have a dependent. And I've identified the type of data as its scale. So on this stats chooser, I've got the option scale dependent variable, ordinal dependent variable, nominal dependent variable, or there's no obvious dependent variable, like there's no dependent or independent variable here. So I'm going to go here to start with, scale dependent variable. Then what I've got to consider is the independent variable. What type of data it is and how many independent variables I've got. So my independent variable here is those who enjoy singing and don't enjoy singing. So it's a nominal and I've only got one of them. So I can go here, one nominal independent variable. So I know now that my stats test is somewhere in this list of stats tests. The thing I've got to choose between now is whether my independent variable has 2 groups or my independent variable has 3+ groups. Right, so don't get mixed up with a number of groups and a number of independent variables. We've got one independent variable and we've got 2 groups. So remember, our 2 groups are those who enjoy singing, that's 1, and those who don't enjoy singing, that's 2. So now I've narrowed it down to these tests. I've got 4 tests here that it's suggesting. The default that we presume is that our data is not matched, right? So a t-test and a Mann-Whitney U is for data that isn't a repeat measure design. These two tests, are for data where it is paired or matched. So we end up knowing that we're choosing either a t-test or a Mann-Whitney U. And the difference between these is to do with you use one if your data is normally distributed and one if your data is not normally distributed. Those are called assumptions and we'll talk about them at the end of the workshop. On to the next study. So it's study B. So the effective time on enjoyment of filling in questionnaires. What I'm going to do is you can access this yourself, so you can scroll up and down. And I want you to, I've given you hints here about all the characteristics of this study B, and see if you can come up with a suggestion of a stats test. So you can stop the video here. Okay, so here's the answers to study B. The first thing we had to do is treat the dependent variable, this how much you enjoy filling in questionnaires, as a scale variable. And remember, that's because we've taken the mean of those 3 questions, so it acts more like scale data. So we're going to say that we've got a scale dependent variable. So we're in this area here. We've got one independent variable. So we know that we're here's one independent, here's one independent, here's one independent. And ours is nominal. So again, we're here. The independent variable this time has 3 groups. So this is a section where we have 2 groups. Now that we've got 3 plus groups, so we've got 3 groups, we're in this section here. So we know that it's one of these questions. And we have repeated measures. So this table assumes that if it doesn't say, if the test doesn't say that it's for data where you don't have repeated measures, then assume that it's for that. It's not for repeated measures. So these 2 are used if you don't have a repeated measures design, whereas this one, as the name suggests, is for repeated measures. So repeated measures ANOVA. And it says there if the data is matched, match is just another term for repeated measures. Just because you have lots of terms for the same thing in stats, just to keep you on your toes. So there you go. The answer is repeated measures ANOVA for that one. So now I want you to think about all these different aspects of study C. You might have noted them down as you went along. If not, have a think about them now. And then use this stats chooser to come up with what stats test you think would work. And then we'll go over the answers. So you can pause the video here. Okay. So we need to think about the dependent variable. And again, the dependent variable is scale. Where we'll come into some examples where the dependent variable isn't scale. It just so happens the first 3 are scale dependent variables. Then we've got to think about the independent variable. Now, in this case, we don't just have one independent variable, we've got 3 here, gender, age, and dog ownership. So it's not this one. It's not this one because this is only where we've got 2. It's not this one. It's not this one. We're down at this option here. 2 plus independent variables. So we've narrowed it down to one of these tests here. We don't have a design where we've got repeated data or matched data or repeated measures. So this one, this option is where one of our independent variables has that repeated measures element to it. It has that matched format to it, and we would be using that test. So in this case, we're here. This is where we want to go. Our independent variables, they can be scale, they can be ordinal, they can be nominal. it doesn't matter. Multiple regression is really good at coping with different types of data in the independent variable. So for that one, a good idea, a good suggestion stats test is multiple regression. Here's the next one. You can have another go at choosing the stats test and pause the video. Okay, so pet preference by gender. If we were investigating this, we'd have to think about the fact that the dependent variable, the pet preference, that's nominal. So we're not here this time because that's a scale dependent variable. This is for ordinal dependent variables, but this is for nominal dependent variables, right? So we're somewhere in this grayed out box. We have one independent variable, which is gender, and that independent variable is also nominal. So here we've got an option of either having one nominal independent variable, like we've got, or more than one independent variable. So here we don't have to go much further. That's the suggested test that we use. But just a note on that, it's really common test, chi-squared. Lots of people are familiar with it, lots of people have heard of it. And that's why we tend to use chi-squared in this situation where we've got both independent and dependent variables are nominal. However, it actually only tests. So this is a bit of stats theory, really. Chi-squared only really tests for an association between the independent and dependent variable, i.e. it's only testing whether as one thing changes, another thing changes, opposed to there being this cause and effect situation going on. So that might just sort of dictate the way that you write up the results of the test. You might want to say that pet preference is associated with gender rather than saying that gender affects pet preference. Okay, last one. See if you can decide what stats test you can choose for this. And pause the video. Okay, here's the answer. For this one, there's no obvious dependent variable. So we're down in this bottom box here. We've got two variables, and those two variables are both ordinal. So we're thinking about this one here. And that gives us Spearman's rank correlation, or there's another option here, chi-squared test for association. And the reason that you might use chi-squared test for association as an alternative is if, like we discussed before, you've got really few ordinal categories. So let's say that everyone that responded to us had really short names, so only 2 categories were filled up. Or maybe everyone was really, really happy about attending a stats workshop, so we only had 4s and 5s in our data. In that case, you're better doing a chi-squared for association. The Spearman's rank correlation, it doesn't really work. There's a summary of which test you would use for which, if you wanted to have a little look at that. Let's finish by talking about testing assumptions. You might have heard of assumptions before, you might not have. They're like criteria, and you've got to meet those criteria in order for the stats test to give you any sort of sensible, reliable answer. So I sort of think of it like these these mathematicians have come up with all these wonderful tests, but they've said, okay, yeah, the tests are good, but they only work if your data is a certain way. They only work if your data meets certain particular criteria. So you've got to make sure that your data meet those criteria, those assumptions of the test. Assumptions are different depending on the test that you want to do. So what I've done here is I've just picked out the assumptions of a t-test, because a t-test is quite a common, straightforward test that some of you might end up doing. So here, the first one is the dependent is scale. So now you should have a good idea of how you tell that, i.e. what variable is a dependent, first of all, and whether that variable is actually scale. You should also be able to tell how many groups you've got in the independent variable. Now remember, that's not how many independent variables you have, right? It's not like our step count example where we've got age, dog ownership, and I've forgotten the other one, gender. That's the number of independent variables. Here, it's the groups in one independent variable. So for instance, in our singing happy birthday, whether you like singing happy birthday or not, we've got two groups there within that one independent variable. The data is not paired. Again, you know that about your experiment, about your study. You should be able to recognize whether it's paired situation or not. Whereas normal distribution, equivariance, and whether your data's got outliers or not, you're going to have to look at your data and maybe do some tests in order to determine these last three assumptions. And there's another really common assumption that isn't one for a t-test, but I think it's worth mentioning because it's common for correlations and linear regression. And that's something called linearity. And as that name suggests, it's whether your data is in a straight line. So I'll briefly go over that. So as always, I like to use examples when I'm explaining things. So that's what we'll look at now. Oh, sorry, before I do that, why are assumptions important? Okay, if your assumptions are not met, there might be an alternative test. So that's what's going on up here, right? So if we want to use a t-test, we have to meet all the assumptions. But if the assumption of normal distribution is not met, i.e. our data is not normally distributed, we have to use this alternative Mann-Whitney U-test. So let's just talk about normal distribution, the assumption of normal distribution, sometimes called normality. You can check it visually just by looking at your data in a graph. So looking at your data in a histogram. And this is how the computer makes a histogram. You get your software to make the graph for you. You don't do it by hand. Imagine we've got data that looks like this. What we do is we take these numbers and we put them into what's called bins, or what you might want to call ranges. Okay, so we've got these ranges along the bottom of the graph here. So 22 will go into the 20 to 29 range, 12 will go into 10 to 19, 37 goes here, 46 goes here, 8 goes there, etc., etc. Okay, so the computer is putting each of our data points into a bin or a range. And then what you see is how common each of these ranges are, right? So we can see that in the middle here, we've got most numbers fall into this middle range. And this is a really simple example, but basically what we're looking for is that when we do this, we get a nice shape like that. And that's quite often called a bell-shaped curve. So a normal distribution should have a bell-shaped curve. I've just done it on one set of data here, but you might have to do it on each group. So for instance, for our happy birthday, singing happy birthday example, we would have to do it on the singing happy birthday times for those people who enjoy singing, and then do another histogram for the people who didn't enjoy singing for their time singing happy birthday. We can also check normal distribution in a test though. So I like doing it visually, but I know that looking at a test gives you a sort of yes or no answer. So what you do in this, what the computer does, computer does all the work for you. The shape of your data is compared to this theoretical perfect bell-shaped curve, right? That's what the computer does. And it can do that in a mathematical way. And all these mathematicians have came up with different ways, slightly different ways of doing that. So what that means is that you could run a Shapiro-Wilk test, or you could run a Kolmogorov-Smirnov test, or you could run an Anderson-Darling test. And there are other tests to do this as well. These are some really common ones to do that. And the way those tests works are that they give you a p-value. And this is how to interpret these p-values. If your p-value is greater than 0.05, then great, you've got normal distribution and you can go ahead and use something like a t-test. If the p-value is less than 0.05, you don't have normal distribution. And in brackets there, I explain why that's true. But basically, if you remember this and this, then you'll be able to interpret these normality tests. Just a little warning on using a test to determine whether you've got normal distribution or not, though. They're not reliable if you've got very small or very large sample sizes. What's very small and very large? Well, we don't like to put numbers on them, but if you maybe had less than, say, 10 data points, it might not give you a sensible p-value. Very large, some people say that if it's over 30, other people say that if it's over 50, then a normality test isn't the best way to check for normal distribution. You're better looking at it visually, or in some cases, you can even assume that there is a normal distribution to the data, and that's called central limit theorem if you think that applies to you and you want to read more about it. This paper here I recommend is a really good plain speaking paper on how to test for normal distribution. If you want to know, sorry, let me make my screen bigger again. If you want to know how to check for normality in whatever software you're using, I've given you guides in the 3 most common software that we use in the university. This one is called Laird website. So if you type in Laird and testing for normality, you should find that. This one's called Data Novia. So type in Data Novia and test in normality. And then there's a statology one here, which you can use if you're a data user. How do you check other assumptions? Well, equal variance is very often checked at the same time as running the test. So that's sort of automatically done in a lot of tests. And then if you want to check for outliers, sometimes you can just flick through data and you can see that there's a really, really big data point or really, really small data. Sometimes it's not that obvious. So you might want to make a scatter plot, and then so you can see that this is an outlier and this is an outlier. Another way is creating a box plot, and then outliers are, there's a mathematical formula used to determine whether an outlier is an outlier, a data point is an outlier, and it's plotted as a circle or a star, depending on what software you're using. The other assumption is linearity. That's common for correlations or linear regressions. And you can use that, and you can check that by creating a scatter plot. So you're plotting one variable against another variable. So these are just 4 different examples. And what we're looking for is that the relationship is, it doesn't have to be a really straight line. It just has to be an approximate sort of straight relationship, if you like. So this, see how this is all scattered? Well, that is what we're looking for. We're looking for, I would consider that as linear. You can put a line of best fit through it if that helps. Whereas something like this, where it increases and then it goes down, it's got like a curve to it, that's not linear. If you put that into a correlation or a linear regression, you're not going to get a sensible answer. And here you can see that we've had to put a line of best fit to see what shape the relationship is, where the best way to analyze this data is not using linear regression or correlation. There's another way to go over this material. We have an online tutorial which goes over the same concepts as what you need to choose the correct stats test, but just using different examples, so it exposes you to different studies, and it also has little tests for you there to fill in.